Hi, in this video we're going to talk about critical values. We're going to talk about what they are and how we use them. Let's go ahead and define what a critical value is. A critical value of a function is a number, x equals c, so it's going to be some x value in the domain such that, and the following two has to happen, one of the two has to happen. The first one is that f prime of c has to equal 0. So if you have any point where your derivative equals 0, in other words, your slope is 0, then you're going to have a critical value. Second, the derivative doesn't exist. So if you have any place on your graph where the derivative doesn't exist, and you remember from a couple sections ago, this occurs at the following places. It can occur at a corner, and the second is a vertical tangent line. These are going to be the two that we focus on for the rest of the video. Let's go ahead and take a look at two different graphs. So here I have two graphs. I want to identify all the critical values on these two graphs. So remember that a critical value can be when the graph has a slope of 0, and so I have one right here. That's a slope of 0. I actually have a slope of 0 right here. You can see it actually flatten out. And then finally we have a slope of 0 right there. And if you come over to the second graph, we also have a slope of 0 right here. So I have four critical values. I'm going to go ahead and mark them with f prime of x equals 0. I'm going to leave them in white so that any of these in white have a slope of 0. Next, we have two critical values over here. So we have one at this point, make that a little bigger. We have one at this point, and then we have one here. Now remember, critical values are actually the x values where this thing happens. So back over here, this x value right here, which I'm going to call C1, that's the critical value. This is actually called the critical point. So we have a critical value at the origin. I'm going to call this C3 for this critical value. So now why is this a critical value? Well, if you look closely and you were to actually follow the slopes of this graph as you're coming in to this point, from this direction, it looks like you'd have a slope about a -1, but if you're coming in from the right, the slopes don't actually match. And what's happening here is that this is a corner. And recall from a few sections ago, anytime the derivative is at a corner, or I'm sorry, if the function is a corner, the derivative doesn't exist. So I'm going to go ahead and mark this as a corner, and this one is also a corner, the same reason. And I'm going to mark it down as the derivative doesn't exist. Now let's go ahead and look at one more graph. Notice what's happening at this point right here. Let me go ahead and circle this. As far as the derivative goes, it does not exist at this point right here, so I'm just going to call that C1, because if you were to draw a tangent line at this point, the tangent line would be vertical. So this is an example of a vertical tangent line. And recall, vertical tangent lines are places where the derivative is not going to exist again. So corners and vertical tangent lines, you're not going to have the derivative existing. So f prime of x does not exist. So why do we care about critical values so much? Well, let's go back to this graph right here. Remember that we had a critical value here, C1, and I had a critical value here at C2, and I had one here at C3. So these are the critical values. And notice what was happening here. We had a slope of 0, but this is also called a local max. Local maxes are like little peaks on a graph. Notice that on the left-hand side, you're actually going up to this point, and then on the other side, the critical value, you're going down. Whenever this occurs, this is actually called a local maximum. So then over here, notice that we were actually going down, and then over here, we're going up. So here, this would be called a local minimum. What's interesting about this is that my local max and local min both had to occur at a critical value. So we have this theorem named Vermas Theorem, and it states that if f of x has a local max or a local min at a point x equals c, so at this critical value, well, we don't know that yet. At the moment, it's just some x value. But if it has a local max or local min at some x value c, and the derivative exists there, then the derivative must be 0. Recall back on the graph a few moments ago, notice that here's a local max and its derivative is 0. Here's a local min and the derivative is 0. So what happens if the derivative was not 0? Well, that would be any one of these other points, like one could be here, could be here. Here's a slope that's not 0, but notice what's not special about it. They're not local maxes or mins. So if you're going to have a derivative exist and it's not 0, then it's just some other point, nothing special. It's not going to be a local max or min. But one thing to note is that just because you have a slope of 0 doesn't mean you're going to be a local max or min. Consider the point right here. All right, at the origin. It has a slope of 0. It flattened out, but it's not a max and it's not a min. Notice that the graph's going down, flattens out for a moment, and then goes down again. So it is not a max or min, but it is a slope of 0. So what does this all mean to us? If you're looking for local extrema being a local max or a local min, what we're going to do is we're going to start by looking for the critical values. Because if there's going to be a local max or min, it must occur at a critical value. And again, not every critical value is a local max or min, but if it's going to be, it must occur at a critical value. So let's go ahead and take a look at those two graphs again we had a few moments ago. So let's go look for all our critical values again. So we had one here because we had a slope of 0. We had one here because we had a slope of 0, C1, C2. We had one here because we had a slope of 0. Here, because the derivative didn't exist, so we'll call that C4. Here, call that C5, or the x value, I mean, because we had a slope of 0. Here, because the derivative doesn't exist. And right here, because we had a vertical tangent line. So that would be C7. So we have 7 critical values on these 3 graphs, but only some of them are local maxes and some of them are local mins, and some of them are nothing. So this is what it all looks like when everything is labeled. You can see which ones are local mins and maxes, which ones are nothing. So now the trick is, after identifying all your local maxes, or I'm sorry, all your critical values, we need some sort of way to identify which critical values are local maxes, which ones are local mins, and which ones are neither. And that will be the topic of the next video.